Hello, welcome to this video. Now let's start with the first power source, solar panels. These are monocrystalline solar panels. We've got two of them, 120 watts each. And we're going to wire them in parallel like this. Since we've only got two solar panels here, I'm not going to use any fuse, not so far anyway, because the total current that will flow during a short circuit here won't be that high, and especially not be higher than what one panel's wires can handle. The short circuit current here might be 11.5, 12.5 amps at most, whilst these wires are often 4 square millimeter wire and can handle 20 plus amps. But if you had, I don't know, say 5 panels, then you would have to reconsider. Truth be told, it might be difficult to even fuse these because you'd need a fuse for each panel bigger than 5.3 amps, but also smaller than the total short circuit, so smaller than like 10. The next step for this drawing will be to add a DC isolation switch. This will allow us to shut the power off coming from the solar panels, much like a tap in the sink. This is especially important for installations with higher voltages. Speaking of voltages, our system is a 12 volt system, or 12.8 to 14.4, never mind, it's called a 12 volt system, and our panels are 22, 23 volts, somewhere there. We don't want to charge the battery with a voltage that high because it will fry the battery. So what we need is something that can regulate the voltage and current. This, a solar charge controller, more specifically an MPPT solar charge controller. This device will take the higher voltage, in this case maybe 23 volts, and step it down, for lack of a better word, to 14.4, 14.6 volts, somewhere there, depending on your battery type, and also the current will go up. But the power, that's to say the wattage, will stay roughly the same, minus any losses of course. Now, as you can see, I haven't connected the wires to the charge controller just yet. This is because the battery needs to be connected first. This way, the charge controller knows what type of battery it's dealing with. In this case, it's a 12.8 volt, 100 amp hour lithium iron phosphate battery. Now we could install or connect the wires like this, and then add a fuse, but we're not going to do that because we have a few more components to add. Because we have more components, I suggest we use a bus bar, which will allow us to connect all our different appliances to one single point, then connect those points to the negative and the positive terminal of the battery. I could make an entire video on just bus bars, but I'm going to try to keep things short. We haven't got a lot of appliances, so something like this will do. These are bus bars with fuses, and they go straight on the terminal. Those orange points are supposed to be the battery terminals. So, something like this. If you're lucky, you don't even have to have a wire between the battery terminal and the actual fuse bus bar object. You can just have it straight onto the terminal. This means one less connection point. This will work fine for us because we are not going to have too many appliances that will overload anything. However, if you want a battery switch there and perhaps a fuse as well, say a fuse that might blow or trip should you use too many appliances, then of course, by all means, add an extra wire between the fuse bus bar and the terminal where you can have your switch and your fuse. Anyway, moving on. As you can see, I've connected the positive to that fuse. We'll discuss fuse size and wire size in just a bit. Now for the negative. We want a normal bus bar. They don't have to be fused. Just like that. Great, now our MPPT solar charge controller knows what battery we're dealing with, what voltage it is. So let's connect the other wires. There we go. Let's pretend it's sunny, so the battery is now charging. As you can see, the amperage is higher than the amperage coming in, and the voltage is lower than the voltage coming in. So far I've used 4 square millimeter wire for the whole installation. This is because, well, first of all, the panels come with 4 square millimeter wire, usually, at least when they're this size, and I don't need anything thicker yet because the current hasn't exceeded 20 to 25 amps so far. Now, 20 amp fuse right there for the solar charge controller, and that's our first charging source. Our second charging source will come from the alternator of the vehicle. Usually you'd have the wires drawn from the battery or the starter battery because that's where you'd connect it most of the times, but I'm just going to keep the alternator here because it tells us the source of the power. Now we can't really just wire things straight from there to the battery, I'm afraid, because, well, one, a lot of modern cars have so-called smart alternators. You might not think they're so smart because of this issue, but anyway, and also our lithium iron phosphate battery is at a different voltage compared to the lead acid battery. It needs a higher charge, so we have to have something in between. Something that will ensure that it gets the right voltage and continues charging until the battery is full, rather than just stops whenever the starter battery is full. This is known as a DC to DC converter or charger, or call it whatever you want. And it looks something like this. At least this model does. So you wire the alternators or the starter battery's wires to the input. Don't forget to add a fuse where the source is, or close to the source. We're going with quite thick wire here, 10 square millimeter and a 50 amp fuse. And this is because even though it says it's a 30 amp charger, that only means that the output is, well, outputting 30 amps. The current flowing between the alternator or starter battery and the input will be closer to 35 to 40 amps. I've noticed in different forums that people tend to get surprised by this. They think it's odd that, well, a 12 to 12 volt DC charge controller would have different currents, but the thing is that it's not exactly 12 to 12 volts. The current will be, the voltage will be a little bit higher on the output side because that's what the lithium battery needs. And also, more than anything, I think losses. The charge controller isn't 100% efficient, so there will be losses in heat, and the current will therefore be higher. How do I explain it? You never get as much out as you put in. Try looking at it as a converter fee or converter toll. Anyway, let's wire up the output. There we go. As you can see, I've used a 40 amp fuse here instead of 50 amp. This is because it's the output side, and the current will be 30 amps. So 40 amps in fuse wise will do fine. Now there are more ways you can charge your battery, but we're going to move on to some appliances, because this is after all a fairly small system. These appliances could be a roof fan, a fridge freezer, a water pump, lights, maybe an electric heater. These small appliances generally don't require 30, 40, 50 plus amps, mega fuses or A&L fuses, or other fuses similar to that. Not always, but many times with 12 volt systems, fuses anywhere between 1 amp and all the way up to 30 amps will be sufficient enough. So I'd use blade fuses for this. And these fit into this type of fuse block. This fuse block will not only act as a distribution center and fuse all your appliances, but it will also make your installation neater, as you only need 2 wires going from the fuse block to the battery's bus bars. So when it comes to mounting the fuse block, you want to put it somewhere easily accessible should fuses blow, and also somewhere fairly close to all the appliances, depending of course on how many appliances you have. If you have lots of appliances, obviously that's going to mean more wire. So try and keep those runs short. You'll have to look at what your appliances use power wise, but for this installation I'm going to say a 50 to 60 amp fuse is more than enough and keeps the 16mm wire safe or protected at the same time. Let's zoom into the appliances. These roof fans usually only draw like 30-40 watts. 30 watts divided by 12 volts is 2.5 amps, so 1.5 square millimeter wire is plenty. We'll talk about fuse size in a bit. Now, we don't need any switch for this one because usually they come with a switch on the actual fan. So unless you really want a switch, you don't really need to add one if it already has one. Next up, the compressor fridge or freezer. Here I've given it 4 square millimeter wire. This is because of the compressor, because the fridge itself might only use about 60 watts. 60 divided by 12 is 5 amps. But these 5 amps could end up being 2, 3, 4, 5 times higher during startup because of the inrush current. So they will draw more currents, but it's just for a little bit, not like constantly. So you don't need to go crazy and have 5 times the wire thickness, but a bit higher, just so that you don't get voltage drops or heat or anything like that build up. I have used too thin wire in the past and the voltage drop was noticeable. Again, here I'm not going to install a switch because the fridge itself has an on button on it, or they usually have. Also, I want the fridge to run continuously 24/7, so there's no point. Next up, the water pump. Here I've used 2.5 square millimeter wire, and again it's because of the same reason. It has a bit of a startup or inrush current, but it doesn't last very long. It's usually not as intense as or I should say, doesn't last as long as the compressor fridges, which is why I've only gone for a 2.5 square millimeter wire here. In my example here, I've got a 10 litre per minute, 120 watt water pump. You could install a switch for this one if you like, but I think a lot of people in RVs choose a more automatic approach, where the pump senses the pressure drop when you open up a tap and therefore switches on and then closes when you turn the tap off, which means the pressure builds up again, ready for use. There are also the ones that have these taps with integrated switches, but yeah, you can also have a manual switch if you like. I think you get the idea with these appliances. I'm just going to take away the heater and just do the light straight away, and that will be it for the 12-volt appliances. So you want to wire these in parallel. That's to say, all the positive wires together going to one point, and then all the negative wires together going to a negative point. Here I am going to install a switch. This is because a lot of lights don't come with switches integrated, and the ones that do, the ones that have like a touch screen almost, I'm not a fan of them, so. Now let's add the negative wires and we're good. Let's discuss some fuse sizes. These are the ones I've chosen. 5 amps for the fan, 15 to 20 amps for the fridge depending on what works best for you, 15 amps for the water pump, and 5 amps for the lights. This is what we have so far, and that's pretty good, but people like to use appliances, and sometimes these appliances don't run off 12 volts, like hair blowers or hair dryers and coffee makers, kettles, etc. So what we need for this is an inverter. In my case, living in Europe, I'd need a 12 volts to 230 volt inverter. It converts the 12 volt DC into 230 volt AC, which is what the appliances run off. In this drawing, I'm going to use a 1500 watts inverter. This is because a lot of these coffee makers or hair blowers use easily 1000 watts plus. That's the ones that use less as well. Anyway, this means that on the 12 volt side, we're going to be drawing a lot of currents because the voltage is low, so the current has to be high. So there we are, thick wire. I'll go into the details in just a sec, or right here actually. So let's say we actually use 1500 watts, and the inverter won't be perfect. It's going to be a bit inefficient, as things in real life are. Say it's 90% efficient, which is actually lowballing it. A lot of inverters are 95%, or maybe even higher. But let's say 0.9 or 90%. That makes 1667 watts on the input side. This means that to produce 1500 watts for the appliances, 1667 watts needs to be drawn from the batteries, or that is what will be drawn from the battery. These aren't resistive loads, these inverters. They're not like a light bulb or a radiator. It's got plenty of electrical components inside it that make it less efficient. But anyway, you can see it as a converter's fee again. So 1667 divided by 12 volts will be 139 amps, which is what you'll be, in worst case, drawing from the battery. But more realistically, it might be like 120 to 140 amps because the hair blower might only use 1400 watts, or maybe your inverter is more efficient. And for this amount of current, you can use 50 square millimeter wire, provided your wire runs aren't like 20-30 meters long. If you keep it to just a few meters, which is more than enough in a camper, then you'll be fine, and if your connection points are good. For this current and wire, I'd go with a 150 amp fuse. One very important note I haven't mentioned yet is that you have to think about what type of battery you're using. In this case, I am using a lithium iron phosphate battery, and these often come with a BMS already installed or inside the actual battery. This is a battery management system that protects the battery in various different ways. One of the ways is from overcurrent. If I'm not mistaken, this particular battery has a 100 amp BMS, I think. It will like shut off or disconnect if you try to pull more than that. And this inverter at 1500 watts will pull more than that, or draw more than that. And especially if you've got the other appliances from the 12 volts fuse block side. So, unless you've got loads of sunshine and you're charging with the alternator at the same time to ease off some of that current being drawn from the battery, this won't really work. You're going to need to have two batteries in parallel so it can draw from both, or just a bigger battery in general, like a 200 amp hour battery. And also make sure that the BMS inside is big enough. Sorry if that made things complicated. Also, if you have a wire running between the battery terminal and that main bus bar fuse thingy-majiggy at the bottom left, then you also might have to fuse, put fuse there if the combined load of the inverter and the fuse block with all the other appliances will exceed that wire's rating, just so you don't accidentally pull too much. If your bus bar is straight onto the battery terminal and you haven't got a wire, just make sure that that bus bar is rated for more than enough current and you'll be fine. A lot of inverters that are on the smaller side will have their outlets on the actual inverter, and all you do is simply plug in the coffee brewer thingy straight into there. The run is very short and a lot of people just have it like that. But larger inverters many times don't have actual outlets on them. They have wire connection points. If that's the case for you, or if you have an inverter as well as camping hookup and you want both of these AC sources to go to the same outlets in your camper van, you're going to need a consumer unit, which looks something like this. But that's for another video.